Now we'll continue with part 3 for the Paleogene and Neogene Earth history for chapter 16. And now we'll start looking at the Basin and Range province. And this region is also known as the Great Basin of the Western United States, and it really encompasses the basins that are east of the Sierra Nevada Front Range, including Owens Valley, Panamint Valley down here, Death Valley, and all the ranges, the White Mountains, the Panamint Ranges, the Black Mountains down here. So you'll see that this region is characterized by basins and ranges, basins and ranges. And so what's going on here is that the crust has been stretched and thinned, and it's dominated by normal faults. Remember, normal fault occurs when you're seeing tensional forces or tensional stresses, and we're seeing that extension in the basin and range. Of those normal faults, we end up getting this large displacement on these range front faults. So in this case, this is Owens Valley, and Owens Valley is around 3,000 feet, and then up here Mount Whitney and the Sierra Nevada is over 14,500 feet. So we're looking at about 11,000 feet of relief, of movement on these faults. And obviously there's been some erosion, so there's probably been even more movement on these faults. So the Basin and Range, mountains bounded by steeply dipping normal faults. And one thing we notice here, so here's the same picture from Owens Valley, we see this scarp. So a fault scarp is the surface break of a recent earthquake. And in 1871, there was a massive earthquake here in the Owens Valley quake of 1871, which was estimated to be magnitude 8.0, so a huge earthquake. And literally there was about 20 feet of uplift of the Sierra Nevada in that one earthquake. And it's really documented by this fault scarp we see that developed during that 1871 earthquake. Now, these fault scarps, so what happens is we have this young sediment here, and then the earthquake happens on the normal fault. Remember, the hanging wall is moving down, the footwall is moving up, and we end up having this step. And again, we know it's a recent event because it's in this younger, loosely consolidated sediment. And we see this eventual uplift of the bedrock here, in this case, of the Sierra Nevada. So what's happening in the Basin and Range, we have these big rangefront faults. Here's Owens Valley and the fault scarp along the Sierra Nevada, the rangefront fault. Then we can have the White Mountains, the Panamint Valley, the Panamint Mountains, and then eventually drop it into Death Valley. All this happened maybe beginning about probably 40 million years ago, but certainly into the Miocene about 16 million years ago. This Basin and Range faulting or extension reaches California, and we start seeing this extension occurring. Also, before the uplift, the Basin and Range had been subtropical, but the Sierra Nevada created a rain shadow. So the rain shadow, in that case, most of the precipitation occurs on the west side of the Sierra Nevada. That's why we see conifer forests here. As that air descends on the east side of the range from faults, it's compressing and warming, causing a more arid climate down here in terms of this rain shadow. So there's several lines of thinking in terms of how the Basin Range formed. One could be back arc spreading, but in this case there's no subduction zone going on. There's no trench rollback, so it's probably not related to back arc spreading. We haven't talked about this, but when the San Andreas transform fault developed, tensional forces developed. It's because the East Pacific Rise, this mid-oceanic ridge, made contact with the trench that was there along western North America. And instead of being a convergent margin, it turned into more of a strike slip or shear forces with some tensional stresses being involved. And some people think that as the Farallon plate subducted, the Pacific plate wasn't being subducted. There was this sort of eddy, or they call it a slab window, a subduction zone window, where you could see magma rising under the Basin Range, causing this extension. Maybe there's a mantle plume in there, but there's really not a whole lot of evidence for that. The mantle plume is really up in Yellowstone. And again, it has to be somehow related to the deformation along the San Andreas Fault. So we'll say more about that in a little bit here. So looking at the Colorado Plateau, it's an elevated plateau. It's around maybe 5,000 to 6,000 feet elevation, flat. We know it has all these Mesozoic sedimentary rocks that were formed during the Cretaceous Seaway. So elevated region, Utah, Arizona, New Mexico. Extensive redbed deposition in the Permian and Triassic. So we looked at some of those Permian age sandstones here in Monument Valley, the Bryce Canyon. These are Paleocene. And there's even some volcanic eruptions that occurred in this region as well. Just a couple more points of it. So we know that during the Cretaceous, the Colorado Plateau had these marine sediments, the Cretaceous seaway. But during the Paleogene, the Laramide orogeny produced folds and large numbers of normal faults. So there's some uplift going on there. And then during the Neogene time, really in the last 23 million years, this region has been uplifted from near sea level to elevations of 1,200 to 800 meters, which is about 5,600 to 6,000 feet elevation. And during the uplift, deep canyons formed, including the Grand Canyon. And although geologists disagree on how these streams formed, whether they were antecedent, and antecedent means they were there before. So in this flat region before the uplift, these rivers were coursing along their paths to either the Gulf of Mexico or the Pacific, or maybe even out toward the Mississippi River. But at some point, the uplift caused these antecedent streams to cut down into that uplifting plateau, and maybe that's how they formed. Or maybe there were these superimposed streams, meaning that the streams established on younger sediment during uplift eroded away the younger sediments, and they cut down into the older sedimentary rocks. A good example of a superimposed stream are the goosenecks of San Juan, and they're often called entrenched meanders. So before the plateau was uplifted, this was lower elevation, and the rivers that established here were these meandering rivers. And those usually form like the Mississippi River, where it's flat topography. But then what happened here during the Neogene period, we saw tectonic uplift of the plateau, but the river maintained its course, and it cut into these sediments and kept that stream shape. So that's an example of an entrenched meander. Now looking at the Pacific coast, remember before the Eocene, we had the subduction of the Farallon Plate. And subduction occurred along the entire west coast of America, really from Alaska down to Mexico, and really down in, by the time we get into the Cretaceous, into South America. And today only two remnants of this Farallon Plate occur. The Juan de Fuca Plate off of California, Oregon, and Washington, and then the Cocos Plate off of Mexico. So when we look at this diagram here, so here 40 million years ago, so here's late Eocene, we see the East Pacific Rise, which is offshore North America, California, Oregon, and Washington. And so note that the plate to the west of this East Pacific Rise is a Farallon Plate, and that's what's subducting in this trench. So remember, this line with the teeth on it indicates a trench where the Farallon Plate is subducting underneath, under North America. And to the west of the East Pacific Rise is the Pacific Plate. And note that that's moving westward, away from North America. So during this time, 40 million years ago, we see a convergent margin here off the Americas. But then the magic number is really 28 million years ago, and that's when we see first contact of the East Pacific Rise with this trench. And for California, it really occurred down here in Southern California part. And what developed here, we developed two triple junctions. The one to the north is called the Mendocino Triple Junction. That's this one here. And today it's off Mendocino, Cape Mendocino, Northern California. And the one to the south here is called the Rivera Triple Junction. And that's this one here. And today it's off of Mazatlan down over here in Mexico. The key thing to remember here is that once we developed this triple junctions, these two, Mendocino in the north, Rivera in the south, where we see three tectonic plates coming together in one spot. For example, the Mendocino, we have the Pacific Plate, the North American Plate, and the Juan de Fuca Plate all meeting at this spot here. For the Rivera, it's the Pacific, North American, and the Cocos Plate all meeting at one point here. But the key thing that's happening is over time, these two triple junctions migrate. In other words, they move away from each other. And as they move away from each other, they make the length of the San Andreas Transform longer, right? So it's a longer distance of the San Andreas Transform. And that's how this thing is developing. So today, that once large Farallon Plate is broken up into Juan de Fuca Plate in the north and the Cocos Plate in the south. So here we have Cocos down here, Juan de Fuca in the north. And that's how the San Andreas Fault really developed, is really the collision of the North American Plate with the East Pacific Rise. And remember, this whole North American Plate is moving westward because we're opening the Atlantic Ocean. So here at Wallace Creek, and Wallace Creek is down by San Luis Obispo, it's called the Carrizo Plain. And here's a creek that comes down here, hits the fault, and then moves in this direction and then comes out. So it's clearly offset. So we call it offset along the San Andreas Fault. If you were walking up the stream valley, you would have to step to the right to get back to its channel. So that's what we call it, a right lateral strike slip. So the San Andreas is a good example of a right lateral strike slip fault. So now just to wrap up chapter 16, we'll look at some of the developments along the east coast. And what's really happening here is we're developing that passive trailing continental margin. We've opened up the Atlantic Ocean. We have a very wide coastal plain. And really towards the latter parts of the Neogene, we see some isostatic uplift where we're lifting up some of these ranges and making the current topography, or this valley and ridge province we see in the Appalachians today. And so here we're seeing Cretaceous, where we have start developing that passive margin. We start seeing erosion in the Cenozoic, and then recent isostatic uplift here in the Neogene period. The Tejas Epirix Sea really affects mostly the east coast. We don't really see it much in the west coast here. And also what's going on is, remember that we had all those evaporites in the Gulf Coast region, the Luan salt deposits. And during Paleogene time, we're developing these salt domes. And remember, those are the ones that are associated with petroleum deposits. So here the Jurassic salt domes are making their way up because they're less dense than the surrounding rocks. And they make these salt domes here in the Gulf Coast region. And again, here we're looking at the passive margin along the east coast. We're starting to see Cretaceous sediments, then the Cenozoic sediments, and we're getting that thick pile of sediments along that continental shelf, developing that trailing continental margin, passive margin. But then it's burying all those old faults that developed, the normal faults that developed from the rifting of Pangaea. So again, the Atlantic continental margin, you got the Cenozoic passive continental margin developing. There's a number of Cenozoic basins that develop in there with younger sedimentary strata. And in Chesapeake Bay, there's evidence of a comet hitting North America about 35 million years ago, because we have this breccia that occurs here. So here is where the impact site would be, at the southern end of Chesapeake Bay. And drilling into the sediments has found breccia. And remember, breccia is angular, fragmented, gravel-sized rock. And so they're all indicating some impact here in Chesapeake Bay region. So anyways, let's stop here for now.